comorbidities and biomarker correlates of disease. Dr. Scott.
First of all, thank you. Second of all, sorry for not changing the title on the slide. I started with an existing slide deck, and so sorry the title is not correct. But it is on HIV Cure, but it's not going to focus particularly on the central nervous system. So these are my disclosures, and the first point, of course, is just a very simple one that we all know, is that HIV persists in cells even during antiretroviral therapy. So this is a nice picture of something we know with a little more detail about the milestones of the HIV life cycle, but regarding the persistence, HIV is a problem, we know, because it integrates into the DNA of cells, and there are also forms of HIV, RNA, and DNA that are either multiply spliced, unspliced, or singly spliced, or DNA that are either 1 LTR, long terminal repeat circles, or 2 LTR circles. And so there's these various forms, and it's these circular DNA and integrated DNA that particularly present problems for us when we're thinking about cure. This is a big table, and I'm going to show you a few big tables, but I'm going to extract some particular information from them in each case, but I put them here with the reference so that you can refer to them easily later if you like. But this is just lists a number of methods that are used to try to estimate how much HIV is archived, is integrated, as well as how much HIV RNA is being used. And so today we're going to talk a little bit about HIV DNA that's integrated, cell-associated HIV RNA, which is distinct from the plasma extracellular HIV RNA that we're all familiar with and is measured in typically blood specimens from our patients in the clinic. There's a substantial amount of work that's been done to understand which are the cells that harbor HIV the most, so that we can target our efforts on them in order to cure people. And this just takes you through, again, information you already know about the progress of T cells from naive T cells to stem cell memory T cells to central memory T cells, transitional memory T cells, and effector memory T cells. And it's these effector memory T cells that we are particularly interested in terms of killing the HIV-infected cells. But the points I wanted to make here is that when we look at the HIV DNA reservoir, these different cells contribute differently to the HIV DNA reservoir, not only in blood in high or low CD4 T cell situations, but also in other tissues. And as expected, we would expect to find more effector memory cells in tissues, and that's the case. But if we target our strategies too much to just one type of cell or one type of tissue, then we won't be targeting the others, and this is part of the complexity of this. And these are only T cells. This doesn't even take into account myeloid cells and other cell lines that can be infected by HIV. So we know, again, part of the trouble here is that when we put people on antiretroviral therapy, this HIV DNA declines very slowly, and this is an analysis from Davey Smith and Matt Strain in San Diego, but others have produced very similar findings, Dr. Silicano from Hopkins and elsewhere, showing that it takes decades for, they model decades for the HIV DNA reservoir to decline. And again, this is an issue not only in blood, like I showed you, but in the brain, of interest to me, but also in the genital tract, in the gut, and in the lymph nodes themselves. So Courtney Fletcher from Nebraska, where Dr. Swindles is from, has looked at antiretroviral drug concentrations, for instance, in various tissues, including lymph nodes, and has shown that the concentrations can be much lower in lymph nodes than in the blood and in other tissues. And so this is true not only for antiretrovirals, but for other processes too. So that's a little bit of an introduction on HIV persistence, and of course we know the good news is that HIV can be cured, and that's based on the Berlin patient. So this was a man, Timothy Ray Brown, who was diagnosed with HIV and started ART in 2006. And as you know, he was diagnosed with AML, leukemia, and received 2 allogeneic hematopoietic stem cell transplants. And the important point here, the important distinction, is that the donor was homozygous for CCR5 delta 32. So remember, this is a 32 base pair deletion in the CCR5 gene, the gene that encodes one of the primary receptors for HIV cell entry. And after he got successfully got his stem cell transplant, he stopped taking antiretroviral therapy eventually, and there was no evidence of HIV in any body fluid or sample tissue, including CSF, I feel obligated to say. So this just shows his viral load over time, and you can see not even a blip, absolutely no HIV, and his CD4 count recovered over time. And so he's remained HIV negative and is thought to be truly cured. So this is not a scalable intervention. We can't give people, ablate their immune system with chemotherapy and give them a stem cell transplantation. Some people would die from that. And so, but there are other cases. There's you'll hear these terms, the Boston patients. These were 2 men who also had HIV with a hematologic malignancy, also got allogeneic stem cell transplants, but importantly, the donors were not homozygous for CCR5 delta 32. And despite that, when they interrupted their antiretroviral therapy, there was no HIV detected in the peripheral blood or in rectal tissue. But that didn't last, and so you can see this one patient lasted almost 8 months before he developed an acute retroviral syndrome and developed fever, malaise, and other typical symptoms of ARS, and was started on antiretroviral therapy. And both of these patients eventually had rebound viremia, and happily they both resuppressed with reinitiation of antiretroviral therapy, but they were not cured. You'll also hear the term the Mississippi baby, and this is a baby who was initially thought to be cured as well, and was thought to be possibly a proof of principle for very early initiation of therapy. So this was an infant born to a woman with HIV and received antiretroviral therapy 30 hours after birth. And the baby initially did have HIV DNA and RNA that met the diagnostic criteria for infection, but the mother was lost to follow-up, and she stopped providing the antiretroviral therapy at about 18 months, and the baby, they eventually did follow-up, and the baby had no detectable HIV RNA off of antiretroviral therapy. And so this is the regimen that the baby received, and you can see here this long duration of suppression. And so you can see plasma viral load, proviral DNA and PBMCs and HIV antibodies remain undetectable through 30 months, but eventually after this article was published in the New England Journal of Medicine, eventually the baby did become HIV RNA detectable after 27 months off of antiretroviral therapy. So quite a long time, but not a cure. So I thought I'd mention one other case of very early intervention. And probably we're going to see more of these cases with expanding PrEP programs, pre-exposure prophylaxis programs. This is Tim Henrich, who also published the Boston patients. But these were 2 men who were starting on PrEP and dealing with an issue that Dr. Mayer was just talking about, that when they came in to start on PrEP, they got an HIV RNA assay, and it was sent out, and it didn't come back right away. And they started on PrEP, and when the assay came back, they were already positive. And they both knew about about when they think they got infected, and it was about 10 to 12 days prior to starting the PrEP. After their test came back positive, they increased their regimen to be a 3-drug regimen. They both, one of them underwent analytical treatment interruption, which is a term being now used for stopping therapy to see if replication recurs, so this ATI, and had, again, a very long duration of suppression without the return of viral replication in this one patient. You can see out to 224 days, again, similar to the baby, about almost 8 months. But then he did recur, but luckily, happily resuppressed on antiretroviral therapy. So it's not to say that very early therapy isn't beneficial, perhaps in limiting the extent of the seeding of the reservoirs of integrating HIV into the DNA, but it's not a cure. So we talk about a few different types of cure. One is the eradication cure or sterilizing cure. That's what we're all aiming for the most part, is to completely eliminate HIV from the body, like Timothy Brown, the Berlin patient. But what we'd be happy to settle for on some level is a functional cure where we don't get rid of the HIV DNA, but the virus does not replicate in people who are off therapy. We almost would be happy in what John Mellors from Pittsburgh here calls a hybrid cure, where people are off therapy and their viral load is reduced and their HIV DNA reservoir is reduced. So that would still be an incremental benefit, but would not be as good as these other two. And this is just a nice graphic showing the difference between these, the typical phases of viral suppression on antiretroviral therapy, and then when antiretroviral therapy is stopped, typically we have treatment failure and people rebound, but this would be a functional cure where people remain suppressed off of therapy, and this would be a sterilizing cure where people are HIV is entirely gone. I'd also thought I'd take the opportunity to mention CMV here as well, like I did in the aging. There's several events. Again, Sarah Janella published this with others from our group, but there's several effects of CMV that contribute to HIV persistence as well. And it raises the specter, the issue of, if we have solely HIV-directed interventions, is that enough, or do we need to take into account other things like CMV also? So what are the HIV cure approaches? You guys know what many of these are. The chief one that's been investigated is latency reversal agents, or LRAs. And this is sometimes referred to as kick and kill, I prefer, but also shock and kill. And the idea is to give the cells something that overcomes that latency, that reactivates HIV RNA, so that the immune system can tell that the cell's infected and kill it. Typically we use something called histone deacetylase inhibitors, Hstack inhibitors, and I'll show you a slide on that. An innate immune component, the toll-like receptor TLR7, an agonist for that is also been proving possibly beneficial. And then once you kill once you kick the cell and start getting HIV replication, then the idea is to kill it. And we may need, I'll show you some data, we may need other approaches in order to activate the immune system too. So enhancing HIV-specific immune responses, either by themselves or in conjunction with a latency reversal agent, is important, and I'll show you a little bit about programmed death-1 molecule, PD-1. There's interest in that, but also therapeutic vaccines and CTLA-4, another gene, another protein. And then gene therapy, actually using gene editing approaches to try to either excise HIV from the DNA or to disrupt other genes or alter other genes that are involved in either protecting cells from HIV or in HIV immunity. And then I mentioned very early antiretroviral initiation as well. So this kick and kill approach, we have this latently infected cell. We use this LRA, this latency reversing agent to shock it. I sort of liken this, and I think others have. I've probably heard someone else say this, but it occurred to me yesterday. I thought it was my idea. You never know. I probably heard it from somewhere else, but it's like kicking a beehive. So I think that's where the kick and kill maybe comes from. You have a beehive, it's sort of quiescent, you kick it, and all of a sudden there's a lot of bees. And I had a patient once tell me that's how he and his kids in his neighborhood used to play when they were children. They would find a beehive and they would kick it, and then they'd run away, and whoever got stung the least won. And I thought that was not a very fun game. You use the LRAs to kick the beehive. As the cell starts to produce HIV, people are on antiretroviral therapy, so that protects uninfected cells from becoming infected. And then this basically causes the cell to declare itself to the immune system, and then the immune system can recognize the cell as infected and kill it. So again, these Hstack inhibitors are one of the chief classes that have been investigated so far, and the histones are these proteins that the DNA wraps around. So we know when DNA is transcribed, when chromosomes are transcribed, they unwrap and open up so that the DNA can be transcribed, and the histones are one of the mechanisms by which that occurs. So again, they're tightly coiled, and then they open up, and they open up in response to acetylation by histone acetyltransferase, or HAT. So the DNA uncoils, transcription can occur, messenger RNA is produced, and then when there's deacetylation by Hstack, it coils back up. So the idea is to inhibit this deacetylation and to force the cells into this open configuration that allows transcription of HIV DNA and other DNA. So there's a lot of agents that have been and are being investigated, and we're particularly interested in, or at least for the purpose of this talk, I'm interested in the Hstack inhibitors. The valproic acid, which we use for seizures and other applications, actually has some activity, but is not a very potent Hstack inhibitor. And so others have investigated varinostat or SAHA, a related molecule, panobinostat, and then romidepsin, a very complex molecule. And the story here is pretty similar in that these agents can be effective in increasing HIV transcription, but there doesn't seem to be a reduction in HIV DNA. So even though they activate the latently infected cells, the total pool of HIV DNA doesn't seem to benefit from that, from the expected killing of those cells. So here you can see the increase in HIV RNA, the kicking, and this is the HIV DNA, so there's no killing. And similarly that was with romidepsin, similarly with panobinostat, we see a similar picture where the proportion of people with detectable HIV RNA, these are people who are on suppressive antiretroviral therapy, it increases with the infusion of panobinostat, and the people who have detectable HIV RNA in blood also have higher levels of cell-associated HIV RNA, supporting that this reflects actual HIV replication. So we're getting kicking, but again, no killing. The HIV DNA levels stay pretty stable over time. So I didn't know this, I just found this out in the last couple of days while I was working on this talk, but these Hstack inhibitors, there's a small literature on them actually, on them inhibiting the cytotoxic T-cell response. So, not only are they focused on activating the cells and increasing HIV replication, leaving the immune system to kill the cells, and as you saw, they may not be doing that very well, but there's actually some data to support that they're actually inhibiting the cytotoxic T-cell response. So this is just showing that these drugs at concentrations that are seen in people actually kill CD4 and CD8 T cells directly in vitro. And then here, looking at CD8 and CD4 cells for the two drugs that I just showed you, romidepsin and panobinostat, you can see that they seem to reduce interferon production by intracellular cytokine assays. And again, both of them do that. And importantly, they seem to, in these series of experiments, they also reduce killing of infected cells. So this is the clone to target ratio. So these are the number of cytotoxic T cell clones. So the larger the number of clones, you'd expect to get more killing. And the target cells, the infected cells, if you have a small number of target cells and a large number of cytotoxic T cells, you ought to kill close to all of them, right? So if you have a lot of targets and low clones, that's bad. So the higher the clone to target ratio here, the more killing you get. But this is the control group here, no treatment, and these others are either the vorinostat, SAHA, panobinostat, or romidepsin. You can see the substantial reduction in killing. So part of the reason why the Hstack inhibitors may not be functioning as well as people hoped is that there may actually be some inhibition by the drugs of the cytotoxic T cell response. So that brings up another area of focus, is how can we improve the antiviral immune response. So again, there's several areas that are being focused on: innate immune response, I mentioned TLR7, adaptive immune response, HIV-specific antibodies, and broadly neutralizing antibodies. That's a very important area moving forward. And then also cell-mediated immunity, and this is just a pretty graphic that summarizes these things and more. I won't take the time to go through it since we're running a little behind. One large area I'm just going to touch on because I want to talk about broadly neutralizing antibodies a little bit more, but this is an important area, are these immune checkpoint inhibitors. So I mentioned the PD-1. So this comes from the cancer field. PD-1 is a mechanism that cancer cells use to evade the immune response. So when a cell expresses PD-1, it's used as a checkpoint for the immune system to tell the immune system that it's a native cell, it's not infected, there's nothing wrong with it, so the immune system doesn't kill it. And so by blocking PD-1, cancer investigators, oncologists have found that they can increase killing of cancer cells. So similarly with HIV, HIV-infected cells express PD-1 to a greater extent than uninfected cells, and so it tells the immune system that this cell does not need to be killed. And so by blocking PD-1 in those cells, that should increase killing. And it's not just CD4 T cells, although that's important, but it's also CD8 T cells and B cells as well. So you can see the benefit of blocking PD-1 on CD4 cells results in more help, as we know, for the T cells and the B cells, greater production of antibodies, greater killing by the T cells, with the result that the productively infected cells will be killed. And so, again, another little table there, like I warned you, but the points here is that there's been a number of experiments that have found that PD-1 blockade may be beneficial. So I'm not going to touch any more on that because we have limited time. But I move on to antibodies and vaccination. So when we think about vaccination, we think about preventing HIV, and that's not the focus for this presentation, but we don't always think about therapeutic vaccination. And so there's more attention being paid to this with the advent of the broadly neutralizing antibodies. And so I'll talk a little bit more about that. These broadly neutralizing antibodies were identified by Dennis Burton and others, and can really very potently inhibit HIV, RNA, and DNA. So this is showing HIV DNA reduction in vitro after an infusion. In vivo in animals after an infusion. And what's very interesting is they compared it to antiretroviral regimens. So you can see here the full decrease in viral load over a 7-day period. So with dolutegravir, which we talked about earlier, 40-fold decrease, efavirenz, 112-fold decrease, raltegravir, 70-fold. this one of the more potent broadly neutralizing antibodies, PGT121, 468-fold decrease in viral load over 7 days. So this seems to be very important, and it's not just in blood; it's in lymph nodes, and again, this PGT121 is one of the more potent ones. So another table, I apologize, but I did this intentionally just to give you something to look at later. I've mentioned the potential importance of using these interventions in combination, and that's what this is meant to show, is that these are current clinical trials as of 2017 that are being pursued, and you can see that some of these combination interventions are starting to appear. And so I'm using that to introduce this very interesting presentation as a late breaker at CROI from Dan Baruch, who does a lot of work in this area. And you can see that they use these fellows like you see on the road from Mumbai to Pune here, and they gave them, they infected them with a SHIV, a simian HIV virus, chimera, and they gave them suppressive antiretroviral therapy and then randomized them to one of 4 other interventions, either giving them sham infusions, placebo, this TLR7 agonist from Gilead that I mentioned, GS9620, this PGT121, or in combination. And what you can see here is that after this dosing protocol, they stopped the antiretroviral therapy to see if they would rebound or not. And of course, all of the animals that got the sham infusions rebounded generally pretty quickly. If they got the TLR7 agonist alone, 10 of the 11 rebounded, so 1 did not. If they got the PGT121 alone, 9 of the 11 rebounded, so 2 did not rebound. But if they got both of them, 5 of the 11 did not rebound after almost 6 months of follow-up. And this is seen here in this survival type analysis. You can see the blue line here is the 2 drugs in combination, and they substantially reduced. And these are small numbers, but nearly half of the animals did not rebound. And what was really fascinating, particularly fascinating, I was very excited by that, but what was even more fascinating is that they took cells from the animals who had transient rebound and those that had no rebound, and they infused them into an uninfected animal. And the animals that did not rebound did not infect the other animals. So the cells from the infected animals that got both drugs together and did not rebound, when they infused their cells into another animal, those animals did not become infected. So, these are very early, small numbers. They're in animals, not in humans, but they're very interesting. So I'll end with just this gene-directed, these gene editing therapies. So as I mentioned, you can either disrupt HIV-related factors or the HIV genome itself. You can add genes, you can edit genes. There's various approaches. And this is just 2 of the examples, something called CRISPR-Cas9 that some of you may be familiar with or heard about in the media, with many, many applications. But what this allows scientists to do is to take something called a guide RNA that can target a particular type of the genome. It can and then insert or alter the DNA at that location. And so these investigators, the same group of investigators from Japan, they used in vitro T-cells and this CRISPR-Cas9 approach to try to disrupt the HIV genome, and they saw about 20 to 40% reduction in the reporter marker here, this reporter molecule, the EGFP DNA. And this was in 2013. I subsequently saw that they have more recent work using another approach called TALENs, and they now have 80% reduction in the HIV DNA in the cell, the reporter DNA. So this is very encouraging, but it is only in vitro. Dr. Tabas also did in people a very interesting approach where he used another type of nuclease, another gene editing strategy, to take people's CD4 T cells and edit them ex vivo to disrupt the CCR5 gene so that they couldn't produce, so it couldn't be used by HIV to enter the cells, and then they reinfused them into the people and they interrupted their therapy. And what you can see here is that the unedited cells, the total CD4 T cells and the unmodified T cells, of course, dropped when they had their treatment interruption, but the modified T cells did not. And you can see there's a smaller number of them compared with the other population, but they didn't decline in response to the treatment interruption, and it appeared that they were not infected. So that's also encouraging us in people. And I'll end with just this other study from also animals using a CRISPR-Cas9 with guide RNA approach and looking at all organs, not just brain, but again, I tend to be very interested in brain. And these are just showing that the gene was inserted into the cells, but you can see a similar substantial decline in HIV DNA here, GAG RNA, and envelope RNA in the cells after the gene editing approach. And this is in brain tissue. So that's very encouraging because, again, accessing these protected compartments can be very difficult. So just to conclude, HIV persists throughout the body despite suppressive ART. Factors like CMV and others may contribute. A sterilizing cure has occurred in one patient, but the method is not scalable, meaning we can't apply it to a large number of people. The kick and kill strategy can activate HIV replication from latently infected cells, but does not appear to reduce HIV DNA, but combination approaches are promising, and a functional cure, I think, continues to be a more achievable goal than a sterilizing cure. So again, thank you to all of you and to everyone who works with us and has contributed to our work, and I'll be happy to take questions.